Hello and welcome to Chapter 3 on Light and Telescopes, which will hopefully be the longest chapter that we talk about at about 140 pages, and is going to go over some of the physics and some of the technology that we use to actually make measurements of celestial bodies in telescopes and other related technologies. Most telescopes work through the absorption and reflection of visible or invisible light, and we have discovered that visible light is only a tiny fraction of the energy emitted by objects in space. Indeed, such phenomena as interstellar clouds of gas and dust, the bodies lying behind these clouds, newly formed stars, intergalactic gas clouds, and a variety of exotic objects such as black holes and neutron stars are nearly invisible to even our best optical telescopes. However, many of these objects strongly emit a variety of non-visible radiation, namely radio waves, microwaves, infrared and ultraviolet radiation, X-rays, and gamma rays that we now have the technology to detect. So far in the textbook, we have used the word light in its everyday sense, the stuff to which our eyes are sensitive. This is more properly called visible light, and it is a form of electromagnetic radiation. Perhaps contrary to one's intuition, this radiation is composed of particles called photons that also have properties of waves. Detecting electromagnetic radiation with telescopes is the essence of observational astronomy. As we go over the different types of light, it's important to start with Isaac Newton, who, as one of the founders of modern physics, came up with the observation and came up with the experiment to prove that white light is not a complete color of light, but is rather a combination of all different types of light. So as you see in the first of these diagrams, when you take white light and put it into a prism, what happens is that the prism will cut the light into different colors that are going to be spread out across a screen that you place there. However, if you place a hole in this screen and put another prism on this other side of the hole, then what you'll see is that when you have that other prism, it will only, instead of taking the white light and becoming white again after you go through another prism, as would happen if you took white light, passed it through a prism, then passed it through another prism without that slit, it will only let through the color of light that is shown to pass through that slit, meaning that what the light was initially is not going to be purely white as we had supposed beforehand, but is a combination of a bunch of different colors of light acting together as a spectrum. The change in direction as light travels from one medium to another is called refraction, and the resulting spread of colors, complete or with colors missing, is called a spectrum, plural spectra. The light that emerged from the first prism was refracted by the second prism, but remained at the same color. The fact that individual colors of refracted light were unchanged by the second prism led Newton to conclude that the colors of a full spectrum, shades of red, orange, yellow, green, blue, and violet — indigo is not considered a separate color in astronomy — were in fact properties of light itself, and that white light is a mixture of colors. To prove this last point, he recombined all the spectrum colors, thus creating white light. Back in the mid-1600s, the Dutch scientist Christian Huygens proposed that light travels in the form of waves. Newton, on the other hand, performed many experiments in optics that convinced him that light is composed of tiny particles of energy. It turns out that both ideals were right. In 1801, the English physicist Thomas Young demonstrated that light is indeed composed of waves. Young sent light of a single color through two parallel slits. He reasoned that if the light were waved, then these waves would behave the same way that waves on the surface of water behave, flowing through similar gaps. In particular, he theorized that the light waves from each slit would interact with light waves from another. For example, when two light waves met, with one wave going up and the other going down, they would interfere with each other and partially or totally cancel out each other, leaving dark regions on the screen. When two waves that are both moving or both seen moving down meet, they would reinforce each other and create bright regions. As we can see from figure 3.2 in the next slide, this is precisely what happened. If light were random particles going through the slits, they would not interfere with each other in this way, and the pattern on the screen would just yield two bright regions, one behind each slit. The analogy with water waves ends here. And in this slide, we see that this interference pattern, which is what it's called, when two waves interfere with each other coming from two slits, which is called a double slit interference pattern, does occur both with water waves and with light passed through two slits, thus substantiating Young's claim. Further insight into the wave characteristics of light came from calculations by the Scottish physicist James Clerk Maxwell in the 1860s. Maxwell unified the descriptions of the basic properties of electricity and magnetism into four equations. By combining these equations, he demonstrated that electric and magnetic effects should travel through space together in the form of coupled waves that have equal amplitudes. Maxwell's suggestion that some of these waves, now called electromagnetic radiation, are observed as visible light was soon confirmed by a variety of experiments. Despite the name of electromagnetic radiation, neither visible light nor any other type of electromagnetic radiation is electrically charged. Newton showed that sunlight is composed of the colors of the rainbow. Young, Maxwell, and others showed that light travels as waves. What makes the color of the rainbow distinct from each other? The answer is surprisingly simple. Different colors of waves with different wavelengths. A wavelength, usually designated by the lowercase Greek letter lambda, is the distance between two successive wave crests as seen on the figure above. The wavelengths of all colors are extremely small, less than 1,000th of a millimeter. To express these tiny distances conveniently, scientists use a unit of length called a nanometer, where another unit you might occur when talking to astronomers is the angstrom, which is 10 to the negative 10th meters. A nanometer is 10 to the negative 9 meters. Experiments demonstrate that visible light has wavelengths ranging from about 400 nanometers for the shortest wavelengths of violet light to about 700 nanometers for the longest wavelengths of red light. Intermediate colors of the rainbow fall between these two wavelengths. The complete spectrum of colors from the longest wavelength to the shortest is red, orange, yellow, green, blue, and violet. Referring to figure 3.1, you can also see that the amount of refraction that different colors undergo depends on their wavelength, which is why when you place white light through a prism, the different colors are going to spread out. The shorter the wavelength, the more light is refracted. Light in vacuum travels at a constant speed c, which is 3 times 10 to the 8th meters per second. The first evidence for the finite speed of light came from in 1675 when Ole Romer, a Danish astronomer, carefully timed eclipses of Jupiter's moons. Romer's discovered that the moment in which a moon enters Jupiter's saddle depends on the distance between Earth and Jupiter. When Jupiter is in opposition, that is when Jupiter and Earth are on the same side of the Sun, the Earth-Jupiter's distance is relatively short compared to when Jupiter is near conjunction. At opposition, Romer found that eclipses occur slightly earlier than predicted by Kepler's law, and they occur slightly later than predicted when Jupiter is near conjunction, meaning that the light that travels when you see these eclipses has to travel closer or less distance when it is in opposition and more distance when it is in conjunction. From his timing measurements, Romer concluded that it takes 162 minutes for visible light to traverse the diameter of Earth's orbit, 2 astronomy AU. Incidentally, Romer's interpretation of the data required a heliocentric cosmology that both Earth and Jupiter orbit the Sun. Romer's subsequent calculations of the speed of light was off by 25% because the value for the astronomical unit AU, the average distance from Earth to the Sun, that existed at this time was highly inaccurate. Nevertheless, he proved his main point. Light travels at a finite speed. The first accurate laboratory measurement of the speed of visible light were performed in the mid-1800s. According to Maxwell's equations, in a vacuum, light travels at a constant speed of c equals 3 times 10 to the 5th kilometers per second, or 1.86 times 10 to the 5th miles per second, which is the same as 3 times 10 to the 8th meters per second. Physicists knew that electrons are bound into the metal surface by electrical forces, and that it takes energy to overcome those forces. Shorter wavelengths of light can knock some electrons off the surfaces of metal, while longer wavelengths of light cannot, no matter how intense the beam of long wavelength light is. Because some colors, or equivalently wavelengths, can remove the electrons and others cannot, the electrons must receive different amounts of energy from different colors of light. But how? Einstein proposed that light travels as waves enclosed in discrete packets, now called photons, and that photons with different wavelengths have higher amounts of energy. Specifically, the shorter the wavelength, the higher a photon's energy, where Planck's constant, named for German physicist Maxwell Planck, has a value of h equals 6.67 times 10 to the negative 34 joules times seconds, where joules is the unit of energy. The photon energy is equal to Planck's constant times the speed of light over the wavelength, or h times c over lambda. Equivalently, because the wavelength is related to frequency, this can be written as h times f, or Planck's constant times frequency. The various types of electromagnetic radiation share many basic properties. For example, they are all photons, they all travel at the same speed, and they all sometimes behave as particles and sometimes as waves. But because of their different wavelengths and therefore different energies, they interact very differently with matter. For example, X-rays penetrate deeply into your body's tissues, while visible light is mostly stopped and scattered by the surface layer of your skin. Your eyes respond to visible light, but not to infrared radiation, and your radio detects radio waves, but not ultraviolet radiation. Earth's atmosphere is relatively transparent to visible light, radio waves, microwaves, short wavelength infrared, and long wavelength ultraviolet. As a result, these radiations pass through the atmosphere without much loss and can be detected by ground-based telescopes sensitive to them. Astronomers say that the atmosphere has windows for these parts of the electromagnetic spectrum. This diagram demonstrates these windows, where optical window and the radio window are mostly transmitted down to the ground through the atmosphere, but you see that less and less of each other type of electromagnetic radiation, where each type of electromagnetic radiation is determined by its wavelength, is going to penetrate less and less into the atmosphere and therefore not be something that we generally see when we're looking from the surface of the Earth. In order to understand and to measure these lights, we use telescopes. There are two basic types of telescopes: those that collect light through lenses, or refracting telescopes; those that collect it from mirrors, or reflecting telescope. The earliest telescopes, such as Galileo's, use lenses, which have a variety of shortcomings as light-gathering devices. Consequently, all modern research telescopes use mirrors to collect light. Lens telescopes refract light directly into the eye of whoever is looking at it. However, mirror telescopes use a mirror at the end, which is called the primary parabolic mirror, to reflect light back towards the middle of the telescope and into a secondary smaller mirror, which is reflected into the eyepiece. A parabolic mirror is selected because any parallel light that enters into a parabolic mirror or into a parabola will be reflected exactly into one place called a focus. This focus is going to be where you place the secondary mirror, or close to where you place the secondary mirror, in order to get the light reflected into the eyepiece or into the sensor that you wanted to look at. So as you see in all of the mirror telescopes on the right-hand side, you take advantage of this parabolic mirror and then use different ways in order to reflect with the secondary mirror or tertiary mirror even, in order to get all of the light that is going through your telescope to focus on a single point. And because light is coming from distances that are so far away, these are essentially parallel light rays, which means that they are going to work very consistently and very well with the mirror and the parabola to mirror into that one focus. You have probably noticed that the secondary mirror of a reflector blocks some incoming light, one avoidable price that astronomers must pay. Typically, a secondary mirror prevents about 10% of the incoming light from reaching the secondary mirror. This problem is addressed by constructing primary mirrors with sufficiently large surface areas to compensate for the loss of light. You might also think that because light is missing from the center of the telescope due to the blockage of the secondary mirror, a corresponding center hole appears in the images. However, this problem does not occur because light from all parts of each object being observed enters all parts of the telescope. Indeed, covering any part of the primary mirror darkens the image but does not limit which parts of the object you can see through the telescope. Likewise, blocking part of the opening of a telescope made just with lenses darkens the image but does not create a hole in the image. Telescopes brighten, resolve, and magnify. As we can see here, if you have a larger primary mirror, it brightens the image that's coming in and gives you a clearer image of what you're looking at by having more data or more light to look at. A mirror with twice the diameter of another mirror has 4 times the area of the smaller mirror and therefore collects 4 times as much light as does the smaller one in the same amount of time. The angular resolution of a telescope is measured as the arc angle between 2 adjacent stars whose images can just barely be distinguished by the telescope. The smaller the angle, the sharper the image. Large modern telescopes like the Keck telescopes in Hawaii have angular resolutions better than 0.1 arc seconds. As a general rule, a telescope with a primary mirror twice the diameter of another telescope's primary mirror will be able to see twice as much detail of the smaller telescope. You can see this increased resolution in the left diagram, and then you can also have a focal length of a primary length of a lens and the focal length of an eyepiece, causing magnification to occur. So different focal lengths are going to cause different magnifications of what you're looking at. So you can have 2 different magnifications with different focal lengths, which are going to give you either the moon on the left-hand side or the moon on the right-hand side. Going back to lenses rather than mirrors, we see the refraction of light going through a different material on the diagram on the left, where as light bends through a rectangular prism of material or a rectangular prism of glass, what it does is that it actually bends and then comes out at a different angle. So what we decided to do as physicists was to grind up these glass pieces into a specific shape which would focus all parallel incoming light into a specific focal point, which is seen on the middle image, and then on the right image all you see is the same difference where going through a material or looking at air versus looking at water causes you to see light coming from different directions. This is also what happens when we look at glasses or our eyes or telescopes or microscopes. All of them use this similar refractory property of glass and of light going into different materials in order to focus light into where it needs to be. One of the problems with this is that instead of using parabolas like we do in order to get a perfect focus, it is somewhat easier to grind lenses up into spheres. And when you do that, the light that comes from the top of the lens is going to have a different focal point than the light that comes from the middle of a lens, which is going to cause there to be different focal points and the light to come at different areas, making it less precise and making the image that you're going to see blurry. There is also a chromatic aberration which occurs because different wavelengths of light are going to go through a lens at different angles, therefore have different focal length, and this is going to cause there to be somewhat different or somewhat stretched out colors when you look at the image that you want to see. We have, however, found ways to account for this, such as using a parabolic mirror instead of a spherical mirror, as stated above, and using a Schmidt corrective plate, which is going to, instead of coming out at different angles, cause all of the light that goes through the corrective plate to come out at a parallel rays. When it comes to actually looking at the data and looking at the pictures that come out of telescopes, we had for a long time just used film or our eyes, but rapidly evolving technology has changed that. We have replaced photographic film with highly efficient electronic light detectors called charge-coupled devices, which work as seen above, where when a photon or a charge comes up to them, they are going to make little marks which you can then use to tell how much light has hit a specific part of the CCD at a specific, coming from a specific area of space. The atmosphere over our heads is moving and changing density, and the starlight passing through it is similarly refracted. Because air density changes rapidly, the resulting changes in refraction make the stars appear to change brightness and position rapidly, an effect we see as twinkling. Another problem with Earth-based telescopes is light pollution, which, as we can see from this picture from, I believe, the 80s and this picture from 20 or 30 years later, is becoming more and more of an issue. So in the picture from the earlier period, we are able to see light because coming from the stars because there is not as much light on the ground, but as we develop more and more cities and more electricity, it becomes more and more difficult to separate out this light and to be able to see it from a terrestrial or Earth-based telescope. To avoid these complications, we have started using space-based telescopes such as the Hubble telescope, whose pictures are seen on the left-hand side of this image, and the James Webb Space Telescope, which has pictures on the right-hand side of the image. Faced with the need, the scientific and engineering communities took on the challenge of developing higher resolutions ground-based telescopes, the need being that it is very expensive to put a telescope up into space, and there is very little time that can be afforded to all of the astronomers that need to look at it. Two types of technologies have succeeded magnificently in that effort, called active optics and adaptive optics. Telescopes equipped with them are more competitive with and often better than those in space. By making thinner mirrors, the shape of the primary optics could be changed by pistons called actuators located under the mirrors. Thus, the field of active optics was created. This technology finds the best orientation for the primary mirror in response to changes in temperature and the shape of the telescope mount. Actuators adjust the mirrors every few seconds to help keep the telescope optimally aimed at its target. With active optics, the new technology telescopes in Chile and the Keck telescopes in Hawaii routinely achieve resolutions as fine as 0.3 arcseconds, where as the resolution is much worse for telescopes without active optics in the same site. The stellar motion due to the twinkling is neutralized by computer-activated motorized supports that actively reshape a smaller mirror installed further down the optical path of the telescope. Adaptive optics effectively eliminates atmospheric distortion and produces remarkably clear images with resolutions as fine as 0.03 arcseconds. Many large ground-based telescopes now use adaptive optics on many observing runs, resulting in images comparable to those from the Hubble Space Telescope. Another method to increase resolution, called interferometry, combines images from different telescopes. For example, used together to observe the same object, the two Keck telescopes have the resolving power of a single 85-meter telescope. The four 8.2-meter reflectors of the Very Large Telescope at the Prano Observatory combine to create the resolution that would come from a single telescope 200 meters in diameter. This observatory has an ideal resolution of about 0.002 arcseconds. In addition to visible astronomy, you also have radio astronomy, which takes advantage of light from a different area of the electromagnetic spectrum. Radio telescopes record radio signals from the sky. Just as mirror reflects visible light, the metal surfaces of radio telescopes reflect radio waves. Each radio telescope has a large concave disk that focuses radio photons in the same way that an optical telescope mirror focuses visible photons. A small antenna tuned to the desired wavelength is typically located at the telescope's prime focus. The incoming signal is relayed to amplifiers and recording instruments. It is then converted into an image. Interferometry, exploited for the first time in the late 1940s, gave astronomers their first detailed views of radio objects in the sky. At least 30 arrays of radio telescopes are in operation around the world. One array, dating back to 1980, still operates on the plains of San Agustin near Cicero, New Mexico. Originally called the Very Large Array, and now upgraded and renamed the Carl G. Jansky Very Large Array, this system consists of 27 concave dishes, each 26 meters in diameter. The 27 telescopes, which can be moved, are positioned along the three arms of a gigantic Y that can span a distance of 35 kilometers. Working together, they can create radio images with 0.1 arcsecond resolutions. The system produces radio views of the sky with resolutions nearly comparable to those of the best optical telescopes. The Very Long Baseline Array, or VLBA, consists of 10 25-meter telescopes located across the United States and at sites from Hawaii to St. Croix on the Virgin Islands. With a maximum baseline of 8,600 kilometers, the VLBA has a resolving power of 0.001 arcsecond. To make radio images more comprehensible, radio astronomers often use grayscales or false colors. The most intense radio emission is shown in red, the least intense in blue. Intermediate colors of the rainbow represent intermediate levels of radio intensity. Black indicates that there is no detectable radio radiation. Astronomers who work at other non-visible wavelength ranges also frequently use false color techniques to display views obtained from their instruments. As with radio and microwave telescopes, infrared and ultraviolet telescopes are all reflectors. Indeed, using suitable CCDs, optical reflecting telescopes can also detect infrared and ultraviolet photons with wavelengths near visible light. The most sensitive infrared detecting CCDs must be cooled to prevent the heat and hence infrared photons of the telescope from overwhelming the infrared radiation received from objects in space. Because water vapor is the main absorber of infrared radiation from space, locating infrared observatories at sites of low humidity can overcome some of the atmosphere's hindrance. For example, the summit at Mauna Kea is exceptionally dry. Most of the moisture in the air is below the height of this volcano. Infrared observatories are made on the summit by the primarily optical wavelength Subaru and 2 Keck telescopes, as well as NASA's 3-meter infrared telescope facility. Some of the finest early ultraviolet astronomy was accomplished by the International Ultraviolet Explorer, which was launched in 1978 and functioned until 1996. Space shuttles were transformed into orbiting observatories twice in the 1990s, carrying aloft and then returning to Earth 3 ultraviolet telescopes. In 1992, the Extreme Ultraviolet Explorer was launched. As with the infrared observations, ultraviolet images reveal sights previously invisible and often unexpected. Many objects in space emit ultraviolet radiation that astronomers can use to study the chemistries of these cosmic bodies. Therefore, in 1999, astronomers launched the Far Ultraviolet Spectroscopic Explorer, which worked through 2007, and the Galactic Evolution Explorer, which worked through 2013. These two telescopes provided information about such things as how much deuterium, a hydrogen nuclei with one neutron, was created when the universe formed, the location of particularly hot interstellar gas and dust, and stellar and chemical evolution of galaxies. Other ultraviolet telescopes are in orbit today. X-rays and gamma rays from space interact strongly with the particles in Earth's atmosphere, preventing these dangerous radiations from reaching our planet's surface. Therefore, direct observations of astronomical sources that emit these extremely short wavelengths must be made from space. Astronomers got their first look at X-ray sources during brief rocket flights in the late 1940s. Several small satellites launched during the early 1970s viewed the sources of both X-rays and gamma rays in space, revealing hundreds of previously unknown objects, including several black holes. X-ray telescopes have also been carried on space shuttle missions. X-ray photons are tricky to collect. Because of their high energies, X-rays penetrate even highly polished surfaces that meet nearly head-on. Therefore, normal reflecting mirrors cannot be used to focus them. Instead, X-ray telescopes are designed to deflect photons at a fairly shallow angle, because X-rays that are barely skimming or grazing a surface can be reflected and therefore focused. This process is analogous to skipping a flat rock on water. Throw it at a steep angle and it will immediately sink. Throw it at a shallow angle and it will skip off the surface. Figure 339 shows the design of such grazing instance X-ray telescopes. Gamma-ray telescopes such as Veritas and MAGIC arrays are also operating here on Earth. As we noted earlier, gamma rays do not reach Earth's surface from space. However, when the photons strike atoms in Earth's atmosphere, they cause cascades of gas particles to rush earthwards at high velocities. As these particles descend into the atmosphere, they give off flashes of visible and UV radiation called Cherenkov radiation. As the Russian physicist Pavel A. Cherenkov first observed, the flash occurs whenever a particle moves through a medium, such as water, faster than light can. Such motion does not violate the tenet that the speed of light in a vacuum is the ultimate speed limit in the universe. Light is slow considerably as it passes through water, and high-emission particles can exceed this reduced speed of light in a medium without violating the laws of nature. This radiation travels predictable angles from the particles that emit, and therefore detecting it enables astronomers to calculate from what direction the original gamma ray came. By looking at all these different frequencies of light, we are able to come up with quite different views of the universe depending on what we're looking at, from radio waves to infrared to visible to X-rays to gamma radiation. There are also other types of radiation or particles which are going to come from the sky other than just photons. Cosmic rays are high-energy particles traveling at nearly the speed of light. They were named rays before their true identity of particles was known, and as often happens, this misleading name has stuck. Cosmic rays were discovered in 1912 by Austrian-American physicist Victor Hess, who received the 1936 Nobel Prize in Physics for his work. About 90% of cosmic rays are protons, hydrogen nuclei, about 9% are helium nuclei composed of 2 protons and 2 neutrons, and the remaining 1% are electrons or nuclei of elements more massive than helium. Cosmic rays are created by a variety of events. Until recently, astronomers thought that moderate energy cosmic rays were emitted directly by powerful explosions of some stars called supernovae. This theory made sense because the explosions were the best known source of energy necessary to give these cosmic rays their tremendous speeds. However, observations by the Advanced Compositional Explorer satellite revealed that the isotopes of nickel coming towards Earth in the form of cosmic rays are not the isotopes emitted by supernovae. Instead, evidence collected by the Fermi Gamma Ray Space Telescopes in 2013 has revealed that many moderate energy cosmic rays are created when supernova debris slam into dust and gas already in space, causing some of this pre-existing matter to accelerate and become cosmic rays. Besides emitting particles, supernovae create gamma rays when cosmic rays protons created as a result of the supernovae smash into normal protons in interstellar space. These collisions create short-lived particles called pions that decay into pairs of gamma rays. Moderate energy cosmic rays and gamma rays from the same direction in space are often detected together, with the gamma rays arriving shortly before the cosmic rays. Much less common than moderate energy cosmic rays are ultra-high energy cosmic rays, most of which come from outside our galaxy. Each of these particles has as much kinetic energy as a baseball thrown by a major league pitcher. While some of these are believed to come from jets of gas called active galactic nuclei emitted by supermassive black holes in the center of some galaxies, the origin of these particles are still unknown. We will explore these black holes and active galactic nuclei together further in Chapter 18. The Sun emits relatively low-energy cosmic rays called solar energetic particles. They occur primarily when the Sun is very active, emitting large quantities of gas as well as its normal electromagnetic radiation. The activity on the Sun will be discussed in Chapter 11. Solar energetic particles are often released in large numbers over short periods of time, tens of minutes, so they can be dangerous to people in space who are not protected from them. Indeed, solar energetic particles pose significant hazards to astronauts, cosmonauts, GPS, and other satellites in space, as well as energy grids on the Earth, and the U.S. National Oceanographic and Atmospheric Administrative Space Weather Prediction Center monitors the Sun's activity and provides warnings as necessary. All cosmic rays in space are called primary cosmic rays, indicating that they were not created in Earth's atmosphere. Most primary cosmic rays and solar energetic particles coming in our direction collide with their gas particles in the atmosphere some 15 kilometers above Earth's surface. This is fortunate because each cosmic ray packs an enormous amount of energy that potentially could harm living tissue. A collision in the air divides the cosmic ray's energy among several gas particles, which are shoved earthwards. These particles, in turn, often hit other gas atoms, creating a cascade of lower energy particles that eventually reach Earth's cosmic surface as a cosmic ray shower. These cosmic rays created from atoms in our atmosphere are called secondary cosmic rays. Their passage is accompanied by the generation of ultraviolet radiation. Because the secondary cosmic rays are moving in slightly different directions than the primarily cosmic rays from which they originate, a single cosmic ray detector on Earth can't tell us the direction from which the primary cosmic ray came. In 2005, the Pierre Auger Observatory, consisting of 1,600 cosmic ray sensors designed to detect Cherenkov radiation created when secondary cosmic rays enter tanks of water on the ground, was commissioned. Located on the Pampa Amarilla, or in Argentina, when multiple secondary cosmic rays strike different tanks, the astronomers can use their paths to calculate the direction from which the primary cosmic ray came. This observatory also has ultraviolet detectors to provide more information about the paths of the secondary cosmic rays. Observations of their paths support the belief that many primary cosmic rays come from active galactic nuclei associated with supermassive black holes. There are now about 10 ground-based ultra-high energy cosmic ray observatories in various countries around the world. By detecting lower energy cosmic rays, it's done by telescopes that are carried high in the atmosphere by balloons and by orbiting satellites, including one attached to the International Space Station. Neutrinos are very low-mass, very high-speed particles that barely interact with other matter compared to the interactions of all other known particles and radiation. Neutrinos are created during thermonuclear fusion, such as occurs in the sun's core and inside all other stars. Because they interact so weakly with other matter, large quantities of neutrinos travel through the entire sun without interacting with other particles along their way. Virtually all the neutrinos created in the sun emerge from its outer layer and travel into space. Very occasionally, solar neutrinos strike neutrons and convert them into protons. If astronomers could detect even a few of these converted protons, it might be possible to build a neutrino telescope that could be used to detect the thermonuclear inferno of the sun's core that is hidden from the view of telescopes that collect photons. Inspired by such possibilities, the American chemist Raymond Davis designed and built a large neutrino detector. This device consisted of a huge tank that contained 100,000 gallons of perchloroethylene, located deep in the Homestake Gold Mine in Lead, South Dakota. All neutrino experiments are performed underground to help prevent them from being contaminated by other sources of energy, like cosmic rays. Because matter is virtually transparent to neutrinos, most of the solar neutrinos that encountered Davis's tank passed straight through it. On rare occasions, however, a solar neutrino hit the nucleus of one of the chlorine atoms in the cleaning fluid and converted one of its neutrons into a proton, creating a radioactive atom of argon. The rate at which the argon was produced was therefore correlated with the number of solar neutrinos arriving at Earth. On average, solar neutrinos created one radioactive argon atom every 3 days in Davis's tank. To the consternation of physicists and astronomers, this rate corresponds to only 1/3 of the neutrinos detected or predicted to be created by fusion in the sun's core. In other words, the theory of neutrino creation predicted one atom argon would be created each day. There were 3 possible explanations for this unexpected result. The experiment could be faulty, the sun might not be fusing at the expected rate, or our understanding of the properties of neutrinos could be in error. This experiment, which began in the mid-1960s, was repeated with extreme care by other researchers around the world who got the same results, suggesting that the experiment was not at fault. Calculations on how much energy the sun must generate as it does confirm the number of neutrinos created per second. This problem had to lie in our understanding of the neutrino itself. Initially, the 3 flavors of neutrinos, electron, muon, and tau, were thought to be completely massless, and if so, the equations revealed that they could not change from one flavor to another. But if neutrinos have even the slightest mass, such as noted above was possible, then they can transfer from one to another. The transformation of such low-mass neutrinos would occur spontaneously, meaning that if an electron neutrino left the sun's core and sped towards the Earth, there would be a finite probability, about 65% actually, that by the time it got there, it would have become a tau or muon neutrino. So if neutrinos have mass, we should observe only 1/3 of them with Ray Davis's detector, because the rest should have changed flavor before they got there. In 1998, the next generation Super Kamiokande neutrino detector in Japan observed the other 2 types of neutrinos coming directly from their sun. Their observations were repeated in 2002 at the Sudbury Neutrino Observatory in Ontario, Canada. The total number of all 3 flavors of neutrinos coming from the sun was as observed by the equations describing thermonuclear fusion. There are at least 28 neutrino observatories in operation around the world and several other under development. They are always also looking for neutrinos from other stars and events such as supernovae. In 1915, Einstein published a set of equations that described the force of gravity more accurately than Newton's law of gravity. Called the theory of general relativity, Einstein's equations predict, among other things, that matter literally changes the shape of the space it is in, and that some of these changes create ripples in the fabric of space-time called gravitational or radiation or gravitational waves, or gravity waves that travel at the speed of light. If this theory is correct, we should be able to detect the effects of gravitational radiation on the objects that emit and also detect the gravitational radiation directly. The most powerful such ripples occur when matter undergoes a quadruple radiation or oscillation as seen on the right-hand side. If one pair of opposite sides moves outward at the same time as the sides halfway between those points move inward, any object that has this kind of motion emits gravitational radiation. These ripples of gravity waves occur in the plane perpendicular to the direction of their motion. The ripples in space-time created by gravitational waves from stars and stellar elements are incredibly tiny. On Earth, each meter-wide volume of space changes less than 10 to the negative 20th meters as the waves created by distant events pass by. Astronomers around the world are building gravitational wave observatories to directly measure these small changes. The detectors each have two perpendicular hollow tubes several kilometers long in which the air has been removed. The longer the tubes, the more sensitive the observation is to gravity waves. A laser beam is split in half as it travels down one of the two beams, reflecting off mirrors at the end of the tube. The beams are then recombined. If a gravity wave passes through the detector, one arm will be stretched while the other is shrunk. These changes are detected by comparing the laser beams that have traveled down the two arms. One beam will be slightly longer than the other, which shows up in the patterns of light when the two beams are recombined.